Okay, so as I was saying, until whatever reason it didn't work, today we will be talking about some things that requires no prerequisite. So please do ask questions if things are not making sense and all that. Okay, so let us first begin by talking about. So we are going to basically the whole goal is to make you write uh, deep learning algorithms from scratch. Okay, so the whole goal is that you will get lab assignments for that. So I want to give you hints and make you understand all the algorithms very clearly, so that when you finally try to implement it from scratch, it shouldn't be a challenge. Okay, so that is what is the goal. So to do that, we need to understand first of all what is a neural network, and what is exactly happening in the neural network and so on. Okay, so all these questions we need to answer, but even before that we need to understand what's a derivative, right? So uh, derivative, we want to understand, right? So derivatives or differentiation, right? So derivatives, so that is the question that we will try to look at. So first, a straightforward, most simplest thing, what is the definition for a derivative from of a function from R to R? There is a limits definition, right? So can someone tell me?
Limit n tends to infinity f dash of uh, x tends to 0.
Okay, yeah, so you tried, that's good. So it is actually this, right? F of x plus h minus f of x by h, right? Tanuja?
Yes, yes,
Yeah,
sir.
so this is equal to f dash of x. So idea is, you have a function, you are trying to approximate that function via a line. Okay, so you are trying to approximate. Okay, let me just try to draw it very clearly. You are trying to approximate that function via a line. Okay, so this is f of x, sorry, this is x, this is x, and this is x plus h, and then you have um, f of x plus h, and this is f of x. So what you are trying to do is like you are trying to approximate this as as well as you could possibly do via a line. Okay, so as you make the h go closer and closer to 0, right, as you make it go closer and closer towards x, you will get what is called as a slope. So this is the derivative in one dimension. Now for those of you in the math department, this is a question for you. So yeah, I want to extend this derivatives. Okay, first derivatives from f of Rn to R. Okay, let's go to the most general case, Rn to Rm. Okay, and I want to extend the derivatives. So what would you say? How do we do this? Have you learned this?
So it will be a matrix.
Yeah. Okay. So how can you define it? Like a very proper way to define. It's a matrix is correct, because first of all, Tushar, I mean not Tushar, but somebody else. So if you take a matrix, does everybody understand that matrix of dimension m cross n? Okay, this is a function from Rn to Rm. Is this known to people? I mean, I have discussed this in the class, I suppose, but is there any somebody who doesn't understand this?
Sir, could you please explain?
Yeah. Okay. So matrix has m cross n dimensions. That means you have m rows, right? So let's say a11 to a1n, and like this am1 to amn, right? Now this is a matrix of this dimension r of m cross n, m rows and n columns. Why is it a function of Rn to Rm? Is that you can take any vector in Rn, let us say x1 to xn, right? So now you can do matrix multiplication. Okay, when you do matrix multiplication, what you will get? You will get a vector in Rm. Is that okay? Do you
Yes, sir.
understand?
So it's like linear transforms. That
Yeah, it is a linear transform. So it's a
yes,
function
sir.
from Rn to Rm. right? So now basically what I'm saying is that f of x, when you have a function from r to r, you replaced it with a derivative is also having the same derivative also, right? F dash can also be thought of as a function from r to r, but the only difference is it's a line. Okay, so when you come to derivatives in Rn to Rm, so this f dash will be a vector from Rn to Rm. Okay, the same, it will have the same shape as this. Okay,
Yes, sir.
all right. So now what is the definition from for those of you who in the math department, right? You would have seen this. So what is the definition of this? Okay, so since you are silent, I'm assuming you don't know or it's too trivial. Do you, Tushar?
Sir, I think so. We call it Jacobian matrix.
Okay.
It consists of partial derivatives.
Yeah, yeah, that is correct. So essentially it is this. Okay, so h tending to 0, you are looking at f of x plus h minus f of x minus here. Let me ask in the chat. What is the dimensionality of x? What is the dimensionality of h? Okay, can someone tell me what is the dimensionality of x in the chat? Rn, right? So everybody understands that. So both h as well as this is this. Okay, so its dimensionality is this. So I am taking this is this norm. Okay, so this is the norm of h. So this ratio, right? So if I take norm on both things, this should go to 0, and then t is a linear transform, or basically it's a matrix of dimension Rm cross n. So let me try to explain what is going on. So you have a function, so x is a Rn. So try to compare this with this. Okay, so let's do some kind of simplification, right? So let's say let me write see, I mean, I'm trying to tell you the whole thing just so that you don't have any fear of this later on. So let's call r of h as f of x plus h minus f of x minus h f dash x, right? So this is h of x. Okay, now yeah, so now if you look at if you let h tends to 0, right? So basically what I'm trying to say is if you let h tend to 0, then what happens? So when you let h tend to 0, this ratio r of h by h, this goes to 0. Okay, so that's essentially what we are saying. Okay, so here here also we are trying to do the exact same thing, just that we can't write f dash of x like this. Limit is a definition which is only in the spaces of R. We want to restrict to R. Okay, so norm what does it do? It's a length, right? It measures the length. So what is the difference between this and your approximation t of x? How much is the difference, right? So that divided by norm. So this is a number. Is this clear, the definition to everybody?
Yes, sir.
Yes, sir.
Okay, so now when you have now coming to whatever earlier people said, right? So let us now try to do properly mathematically how should each of the derivatives be, right? So now one by one we will see, and then we will come to back propagation and then trying to write the code for it. All those things we will try to address. So if you take a function from Rn to R, right? So what should be the gradient f dash? What should be the f dash shape be? What it should be? I told you. So what is it? Yeah.
1 cross n.
Yeah, so
1
this,
cross n.
yeah, so this should be a matrix of dimension 1 row and n columns. Okay, so that is the gradient. So this is what you have already studied, which is called as a gradient. Okay, gradient of f, and that is written as grad f. So very mathematically properly, if you want to write it, it is this. So partial derivatives with respect to x1, partial derivative with respect to x2, all the way till partial derivative with respect to xn, right? But when you have studied, when I have also taught you, the typical convention is to write it in a column wise manner, but if you want to write it mathematically correct, you have to write it in the row wise fashion. Okay, is that all right?
Yes, sir.
Okay.
Yes.
Okay, now coming to, so this is the gradient of f. Now as Tushar told, see, why is this gradient? If you actually plug in these values here and if you evaluate this limit, it will turn out to be 0. That is why it is gradient. Okay, so that is something that we will not be able to prove it this class, because that is too much of calculus, more than what I would like to explain. But the point is clear, right? You put this matrix as T and try to evaluate this limit, right? So this norm is an operator that gives you a single number, right? This ratio gives you a 0, that you can formally prove. Okay, so that we will not do, but it is something that you can check, I mean, if you are interested. Okay, so can I just see so far if people are following? Any questions so far? Sejal and Tanuja?
Yes, sir.
No, sir, it's no
Sir,
question. It's
I have
clear.
one question. In the
Yeah, yeah, it's Tanuja, go
Sir,
ahead.
I have one. Yeah, in the previous first like R to R case, we had
Yeah,
f dash of x. Like
yeah.
the limit is equal to f dash of x. What is similar to that in n cross n Rn to Rn case?
So that is T here.
Okay.
So
Yeah.
T is, because if you multiply by this and that gives you R of h, so R of h by h goes to 0. Okay, this is equivalent to this, saying this, right? Okay, in that sense,
Yes.
yeah, in that sense we are saying. Okay, so okay, is it clear now?
Yes, sir. Got it.
And you also understood why the gradient has to be in this shape. It should be a row vector.
Yes,
Is that
sir.
okay? Okay,
Yeah.
all right. So now let us talk about gradients in higher dimension. So f of Rn to Rm, right? So this is a little bit of a complicated thing. So so it is complicated in the sense because there are too many things. You have to take slowly. Okay. So what we will do is, first we will look at fi, only the ith component. Okay. So ith component, if you see, it is a function from Rn to R. Yeah. Yes. I am only looking at the ith component of this vector. Okay, how many components it will have? I takes value what, from 1 to how many?
1 to m.
1 to m. Okay,
M.
so yeah, so what is gradient of fi?
Psi f
Partial
I
derivative
x.
of
Yeah, yeah. So del fi xi, x1, del fi x2.
x2
Yeah,
till
yeah.
del f I xn.
Yeah. Okay, so this you all understand. Now the overall gradient of f, right? So df by dx, this is going to be just putting all the gradients one on top of each other. Okay, so the first will be gradient f1, gradient f2, all the way till gradient fm. Okay, so dimensionality, so this is going to be a matrix whose dimension is R m cross n, m rows and n columns. So this is also, so df is a function from Rn to Rm. Okay, as we wanted. Okay, so this, it has to be Rn to Rm. We are also having Rn to Rm. This is actually the total derivative. This is called as the total derivative. Okay, so far is it clear to everybody?
Yes, sir.
Yes, sir.
Okay, okay, good. All right, so now this is about all the derivatives that we would require for this class. How are all the master students? Are you able to follow so far, Shreyans?
Yes, sir.
Okay,
It's clear.
okay. So now let's talk about next important thing that we will need, which is called as a chain rule. So chain rule. Okay, so let's say you have function f r to r, and then you have g which is r to r, right? Then you have some h which is f of g of x. Okay, so h is also a function which is from r to r. This is composition. It is composing two things one after the other. Okay, now what is df by dx? What is df by dx? Sorry, not df by dx, dh by dx. What is dh by dx? In terms of
df
df, yeah. Sorry, tell me.
df by dgx into dgx by dx.
Okay, there is that is not exactly correct, but you have to say like df by dg, but f is evaluated at g of x. Okay, and then dg by dx, right? So this is the more correct way of saying it, right?
Yes, sir.
Yeah. So it is also not a hard thing to check. Okay, so let us try to check it, because otherwise, so typically we don't write it like this. We write it as f dash of g of x times g dash of x. This is how we write it. Okay, so we don't write it in the way that I have written, so like this, but you write it more like this. This is what you are more used to seeing. Okay, so let's just look at a quick proof of this, simply because we can do this. Okay, so it's not too difficult. So dh by dx, if you remember the limit, this is like h tending to 0, h of x plus h minus, sorry, not h of x plus h, it is f of g of x plus h, okay, minus f of g of x by h. Okay, so what we can do is we can write this as limit f of g of x plus h. What we should write it as to get what we want?
Multiply and divide by gx plus h minus dx.
Yes. Now you introduce a change of variables. So what you do is you call this g of x plus h as y. Okay, so this you call it as y, then this will be y plus h, small, because as h tends to 0, maybe h dash, not exactly h. Okay, so what you will get is limit f of y plus h dash minus f of y divided by h dash. Okay, as h tends to 0, h dash also tends to 0. That limit times this limit. Okay, so this you can do, and this gives us back. So this will be f dash y times g dash x. Okay, and this y we have already said that it is equal to g of x, right? So f dash of g of x times g dash of y, g dash of x, right? So this is essentially the proof. Okay, so these are all things that you have seen in school. I am just reminding you, just so that you get comfortable with these objects. Okay, so now chain rule in higher dimension. So chain rule in higher dimension, so let us write that. So you have let's say a function which goes from Rn to Rk, and then you have G which goes from Rk to Rm, right? And then H is a function which is composing these things together, right? So G of this, so H is a function that goes from Rn to Rm. Is that all right?
Yes, sir.
Yes.
Sir.
Okay, so you start from Rn, go to Rk, and from Rk you go to Rm. Okay, so that is what it is. So now so what is the dimensionality of the derivative, total derivative of f when you
K cross
evaluate?
N.
Yeah, this is going to be k cross n. Okay, and this will be belonging to
M cross K.
m cross k. Yeah, right. So basically when you take h, okay, so when you try to take the derivative of th, the chain rule is going to say you take tf evaluated at g of
Sir,
x.
TG evaluated at f of x. Right?
Yeah, sorry. Yeah, correct. So tg evaluated at f of x times tf. Okay, so basically you are multiplying two matrices, one whose dimension is m cross k, another one whose dimension is k cross n. So the resulting dimension of th will belong to R of m cross n. Okay, so is the chain rule clear?
Yes, sir.
Sir.
Yes, sir.
Yeah, so this is going to be matrix multiplication. Okay, so let me just write it here. I don't know, there is no notation for this, but yeah, I will just write dot, but this is matrix multiplication. Okay, so these are all the prerequisites required before we start trying to answer the question, how do we do the back propagation? So why I'm going into so much detail is because you have to be able to code it, and that is going to be one of your tasks. Okay, so first, what's a neural network? Let's understand that. So what you have is you represent, there are several operations that you can do. So you take all your dimensionality of input as your input layer. So this is x1, x2, this is your features, x1, x2, xd, this is your features. Then you have various neurons, so let's say there is k of them. So what that does is, it does here you have, let's say, some bias b1, b2, bk, right? So what you are doing at this point is you are doing w transpose x, okay, and here in the second layer you are doing w transpose x again, but with different parameters. So this is w1, w2, okay, like this. So this is what is the purpose. You are doing a series of operations at each level, and then after this you may just pass it through sigmoid function, right? So sigmoid will, what sigmoid does, you know, it will do sigma of this. Okay, like this you are doing several operations one after the other. Okay, so that's essentially the neural network. There is nothing too complicated. All you are doing is you are doing a sequence of operations. Okay, I don't this is not a good picture for you to keep in mind, but it will be useful to, I'm just defining here what is a neural network. It is just basically a sequence of operations that are done at various levels. You can represent it as a graph, okay, and the graph will have this kind of a operation defined on that graph. You tell very clearly what that layer is going to do, and that is what is defining one layer. If you put multiple layers, that becomes a deep neural network. Okay. So ultimately, after all these layers are put together, finally you will have one output, which is your prediction, right? So this will be either your prediction for the house prices, or it will be your prediction for your classification problem. And then you can, if required, you can have an evaluation layer where you are computing the loss. This can be computed. You supply what is the y given, and then you try to find out the loss. Like this, you can put together all these things, and you try to minimize the loss. Okay, and you try to minimize the weights, which, I mean, you try not minimize, but try to adjust the weight so that the loss is minimized. Okay, I don't know if this is requiring more discussion, but shall we just move on? Is this clear to people what is happening?
Yes, sir.
Sir, I think there is a doubt in chat.
Yeah, so let me see that. X1 to B1 is a single function, or are they different functions? X1, so let me see what I have written here. So these are different. B1, B2, BK are different.
No, sir, as in these lines are the functions, or like?
No, the lines just say these are the input to that functions. So when I draw the lines, I am saying that x1, x2, xk, they are going as inputs to this function.
Okay, so X are not functions, B's are functions.
No, this box is the function. B is the bias. So at the output here, I will have W transpose X plus B1. Did you understand? So this is also an input that you are setting. B's are not the function still. Siddhant, is that clear?
Okay, so sigma, the sigmoid is the function, and we are doing this transformation before we give it.
Before we give it to it. Exactly.
Okay, sir. Thank you,
Okay.
sir.
Yeah. Okay. Yeah, there is something else in the chat, I think. Let's see.
Sir, I just wanted to confirm. So each layer is essentially a set of functions who are receiving the input from the previous layers or previous functions.
Yeah. So each layer is going to receive inputs from whatever is computed here, and it will get here, and then you will compute something and you will pass it on. Okay. This is one architecture. So we will focus first on this architecture, and then we will see, if possible, we will try to do different types of architectures.
Sir, will we be covering convolution?
Let us see. I mean, it depends upon how much time we have and all. I'm planning to do as much as possible, but let us see.
So, what is the essence of this transformation in between the layers?
So you are just doing you have, okay, so let us look at first, anyway I was planning to do this. I was first going to tell you how to do this linear regression first in this architecture, and then I was trying to say more, but the idea is this, right? So you are trying to, instead of trying to learn one behavior, you are trying to construct different intermediate function outputs. So this is your, see, if you look at an image of 5, right, versus 0, right? So here there is a region which is closed, right? There is no edges and everything, whereas here 5 is consisting of several edges. There are these edges that are coming in, right? Here there is no edge. So idea is, like, when you are taking some function here, hopefully this will try to learn if there are edges, if there are any horizontal edges, right? If this will try to learn if there are any vertical edges, this will try to learn if there is any closed area. Do you understand, Tanuja, what is happening?
Yes, sir.
So then, see, you are trying to see, you don't know what you want to do, right? So you are allowing the machine itself to find out what are all the features that are best it can learn to identify the ultimate output. That is the idea of neural network. But when you actually deploy it, it doesn't necessarily do this. Okay.
Yes, sir.
Are there any other questions?
Yeah, yes, sir.
Yeah.
Particularly now that this example you gave, that this particular someone will be looking at the vertical edge, someone will be looking at the horizontal edge. Since we are not coding them separately, like this is being like they are learning it on it themselves, there are chances that they learn only the horizontal edges, or maybe they miss out on the some diagonal edges, well, like whatever it is.
Yeah, yeah, that is true. So that is why people are a little bit afraid to use neural networks, deep networks, right? Because you don't have any interpretability, you don't understand why it is working. At the end it works well, but why is it working, that is always been difficult to understand why it is working. Whereas if you look at linear regression, you always know that there is a weight associated with every feature. Some features are more important, so that way there is a clear understanding. Somebody can say, okay, that is the reason why we are giving more weight. But this particular thing we cannot really say because there is no clear interpretation. Siddhant? Is this okay? I mean, shall we continue? Am I online?
Yes, sir, you're audible.
Okay, so does everybody understand the idea of what is happening here? Okay, are there any other questions? All right, so I will move on to the next thing which I wanted to do, which is basically,
Excuse me, sir.
yeah.
Sir, there was a power cut at hostel. Could you repeat what you said for the last 2 minutes, please?
Okay, so where were you? Did you see the chain rule in higher dimension? This derivatives and everything. Did you follow?
So the last question that Siddhant has asked, you are talking about it.
Yeah. So Siddhant, that was what Siddhant was asking is like. So I gave an example where the neural network is trying to learn intermediate features, right? So he asked, what is the interpretation? So this all started when Tanuja asked, why are we doing this? What is the goal? So for that I said, like, if you consider the handwritten digit recognition, if you don't think of it as a machine learning problem, but if you think of it as an engineering problem, what you can say is like for the recognizing 5, right? There are 2 edges that are here on the horizontally, there are 2 edges and 1 vertical edge, right? So that way you can say you can recognize this 5. If there are these things, you recognize 5, whereas if there are no edges, you recognize 0. Now the motivation is each of these layers here is hopefully going to focus on one aspect. This layer may focus on vertical aspect, this layer may focus on horizontal aspects, right? And this 0 that may be focused on some other neuron. So that is the goal why people have come up with this. Advay, is that okay? I mean, you missed the
Yes, sir.
now it's clear, right? I mean, I didn't progress much, I
Yes,
think.
sir.
Okay, Siddhant, you have.
So, yes. Yeah, sorry, sir. There was a power cut here at the hostel, so I just got disconnected for a while.
Okay.
I just wanted to confirm. So, as you mentioned, that this is so there is some sort of ambiguity, right? We are not sure what each of these nodes are actually doing. We are just
We are just hoping for the best.
Well.
Yeah. You're right. Absolutely
So,
right.
can you later on check what they are doing? Like, for example, in linear regression, we can simply check, okay, these are the weights, that are the final weights. The most optimized weights are these.
Yeah.
So can we later on check if this is checking for vertical or horizontal?
No, you can check, but typically you will not be able to make out anything at all. Okay, so how it happens is that you will not be able to make out what is going on. You can check, but it will not. I mean, if what I'm saying is you can hand design these weights so that it detects this. This humanly you can do, but when the machine does it, it will not be meaningful for us. Siddhant, do you understand what I'm saying?
Yes, sir.
You can visualize, right? I mean, what is there to visualize? You just give an input to this layer and see what is its output. But if it is detecting this, what will end up happening is it will emphasize these things more, right? Whereas when you actually run a neural network training, you will not see these kind of prominent edges. That is what you will end up seeing. Okay, it will not be useful at all, but it still works. So that is why theory of deep learning is something people are trying to study to understand why it is working and so on, right? Okay, so
Yes, sir.
yeah, so let's move on. So basically now what are we trying to do? I just gave you a definition of a neural network very informally. There is nothing more than this. It's essentially composed of various computation layers. It takes the inputs from the previous layers, as Shreyans told, and it does some operations and passes it. Okay, that's all it is doing. Okay, so let us look at this. Let us look at a simple regression first, and then once you understand regression, everything will become more and more easier. Okay, so let's look at regression first, and from there we will see what else we can do. Okay. So let us look at linear regression. Linear regression as a neural network. So I am treating, even though linear regression is not a neural, yeah. Yeah, Tushar, you said
Sir,
something.
in the neural network,
Manthan?
excuse me, sir.
Yeah.
So, sir, that in neural network X1, X2, XD are different features, right?
Yeah. So
So,
these
sir,
are,
are they vectors like the vectors?
yeah, they are vector. This is a vector. So this is for the ith input, right? So this is the ith training example. So Manthan, it will become very clear when I look at an example. Okay. Is there some?
Okay, sir.
Yeah. Is there some network connectivity problem in hostel still? Some people have dropped off.
Yes, sir. There is a power cut in the hostel.
Okay.
Yes, sir. We are.
So I am Tushar, speaking from Manthal.
Okay. Yeah. Okay. All right. Anyway, so it will be available for you as a recording later. Anyway, so let us try to do that. So instead of trying to draw this complicated, blobs and everything, so we will use an alternative approach, which is like this. So what you will do is you will write an hexagon to denote one type of operation. So this operation, what does it do? Let me try to explain. So input is X and W. This is your parameter, and output will be, let me call the output as N. Okay, so what is N? N is equal to XW. Okay, so let me write what is X and what is W very clearly. So X is X11, X12, X1D. Okay, so and X21, X22, X2D, and this is XN1, XN2, XND, right? So there are the D different features are there. This is for training sample 1, training sample 2, training sample N. Okay, and W right now I will take it as a simple row vector. Okay, so let me call it as W1, W2, W3. Okay, so so when I do XW, my output will be a row vector, which is N, which is
Sir, W should be till WD, right?
yeah, WD, sorry. So basically it will be your linear regression predictions that you have. Okay, I will not write it, but you understand what it is, right? So I'm multiplying this. If you want, I can write it, but X11 W1 plus X12 W2 and so on, right? So there will be D of them. So this is what it is. So then we will pass it through another layer, which is the bias layer. Here we will add a bias B. So this bias, so what it will do? So it will produce a value P, okay, and P will be equal to so the N1 plus B, N2 plus B, N small n plus B, right? It's just adding a bias, same thing it is adding. This is linear regression, remember? So now then we will put it through another function, the gamma. What is the gamma function going to do? It is going to compute the loss. Okay, and loss is going to be summation. So this P has n components, P1 to Pn. So it's going to compute pi minus yi squared. Okay, I equal to 1 to n. So this is a simple neural network. Is everybody with me? Are you convinced that it's a simple neural network? Yes? No?
Yes, sir.
Yeah, it is
Yes,
just
so
to.
what does V means?
Sorry. V
What
is
does
an.
V represent?
V represents the matrix multiplication.
Model.
Matrix multiplication. Alpha represents adding bias. This lambda represents computing the loss.
Laws. Okay, sir.
Okay. Now the goal for the next 10 minutes is to compute the derivatives at all the points. Okay. See, now one thing you have to understand is that if I try to so I need to be able to compute these derivatives. I am interested in which derivatives? I am interested in dl by db and dl by dw. Okay. For this algorithm, I am interested in dl by db and dl by dw. Why?
Those are the inputs.
Those are the parameters that are under my input. Yeah, so I have to do gradient descent. You remember what was the gradient descent step? So what we will say, f of f what is that? W n plus 1 is equal to w n plus descent, right? So you want to minimize the loss, so you have to go in the negative gradient direction, minus eta times grad w, the gradient of w, right? So this is what we used to do. So batch or stochastic, we want to do this, right? So we want to tweak b, we want to tweak w, and we want to be able to estimate this so that we can do this. Okay. Now I am saying these two, everybody understands why this is important. I am saying this is also important, dl by dx. Can someone tell me why? In the you first think about it for some time. Don't just tell the answer right away, but just think about it. I want you all to ponder it. But yeah, so who would like to tell me why dl by dx is important? This is important for gradient descent. Why is this important? Are you all following so far? Whatever I have discussed, is it clear? This point here, is this clear to people why dl by db and dl by dw is important? Yes.
Yes, sir.
Yes.
Okay, so just that you are not able to think why dl by dx is important.
Sir, I guess it should be important in a way like if we give data in a different sequence or different manner, like interchanging first to last and randomly assigning.
Okay, it is almost correct, but the point is in a neural network what you will end up having is that this will be one of the layers, right? So in the future when you will see you will have many of these things put together, right? So there is this is the actual input x, but the input to this is not x, this is some output 1 of the first layer, right? So there are many layers that I have not drawn, many layers, many other layers, but all these things will form, this will be like one layer. So many other, not layers, but many other neurons like sigmoid, ReLU and things, right? So these things will be there. But what I'm saying is, see, ultimately it will be chained together. Finally, you will have the loss function. So when I try to tweak W, what does it change? If I change W here, what does it change? Does it change this W here? This W is different. No, this W is different from this W, right? This is W in the layer 1, this is in layer 2. If I change W, this will not change. Yes? Tushar, are you able to understand
Sir,
what I'm saying?
why it is not going to change? Like we are passing the value x wx right in the
Yeah,
forward layer, so
yeah.
it should change.
No, it will
Like there
change
is
this. It will change O, but this is another set of independent parameters. These are independent parameters. You can tweak them way you like, but this parameter you can't tweak. If I change W, I will end up changing this.
matter.
You got it right?
Yes, sir.
So therefore, we are also interested in DL by DX because this could be part of a large neural network. This could be a part of large neural network. Okay, when you go to large neural network, this is also we are interested in. Okay, are you following so far whatever I'm saying?
Sir, yes, but if we have a single layer, then DL by DX won't be.
Yes, if we have a single layer, it is not important, right?
Okay.
Absolutely. Okay, so that's good. So now let's try to systematically try to get derivatives at every point, right? So first of all, what happens at every layer is very clear, right? So I do xw and I will get n, and once I get n, I don't care about the previous layers. This layer, so every layer in the, okay, so there are two paths. Okay, there are two distinct paths. Okay, so in the forward path, okay, what I'm saying is once you compute an output and pass it to the next layer, that's it. The next layer doesn't care about what operations happened before, right? So forward path are like kind of independent. Do you understand that? So once you compute something and get a value, that's all the next layer wants. It doesn't care how you got those values. It will just do some operation and pass it to the next layer. So that way the layers will continue. Okay. So forward paths are independent. So what is the backward path? Backward path is where the derivatives are computed. So this we have not yet seen. We will see it tomorrow. But backward paths are also independent, which means you do some operation and pass it back. This is for computing the derivatives. So you do some operation, pass it back. That also will be independent. I have not yet shown you how, but I will do it tomorrow. But backward paths are also independent. So put together, you will have the entire neural network. Okay, so that is what it is, and I will try to explain how do you compute DL by DB, DL by DW in the next class. Okay.
Excuse me, sir.
Yeah.
Sir, by independent, like, is the do you mean the forward path is independent of the backward path, or
No, independent is not in the probabilistic sense. Okay, this is from the sense of like programming, right? You don't really care how you got these values. You just do something and you pass it to the next guy. It is not like I don't have to, if this input has changed, input architecture has changed a little bit, my part is I am okay with that. I don't care what input architecture, if there is something has changed, I don't care. Is that
Okay,
clear?
sir. Yes, sir.
Okay. So that will also end up being true for the backward path. That is what we will do in the tomorrow's class, tomorrow at 3. Okay. So I want you all to go back and check all of these things and see if you understand each aspects of this, and think of ways yourself how you will do these. And basically this will require chain rule. So think of the chain rule. Try to find out what is DL by homework, which I will anyway do tomorrow, is try to find out what is DL by DP, right? So try to find out what is DL by DP, what is DL by DB, DL by DN, all these things you try to think of. Okay, tomorrow we will do it anyway, right? So this is homework to think about. Okay, so you can try this. So if there are no other questions or anything, we will pause here, we will stop here. Let me just stop the recording, and tomorrow we will pick from here. Okay, all right.